For what we're doing today, our control to a goal pose, really our only assumption here is that we're going to assume that the pose is possible first. We're also going to assume that the exact path is not important. In general, you can do things like optimize for time, path distance, energy consumption, gentle curvature, so that would be like making sure that your path doesn't require you to take sharp turns. Instead, you do something a little bit more gentle. But we're going to look at the simplest version of this possible today. And we're going to do so by first breaking this down into two steps. We'll first talk about controlling the orientation. And then we'll talk about breaking this down into separately controlling the position itself. So what do I mean by orientation control? Simply what I mean is that we're not going to care at all about the position. That's going to be entirely unimportant. And instead we will only care about the orientation. And so we'll define the orientation as our angle theta, as determined by the angle between xg and xr. The nice thing about our differential drive robot is that we can directly control the orientation without changing our position at all. So we're going to come up with our control law for orientation control. And that's going to require me to first give us a goal orientation. So let's say that our current orientation is theta. We could, for example, want our goal orientation to be this orange value. And I'll call that theta lowercase g for the goal theta. So probably not too hard to imagine, but essentially we want the robot to be facing in the other direction when it's all said and done. About like that. And for that we're going to use a proportional control law. Specifically, we want to minimize the error between these two values. We want theta to be equal to theta g. So I'll first define a value for the error. And we'll set that equal to theta for the goal minus our current value for theta. And of course we don't have to define it that way. I just find it easier to define it in a way such that if theta g is larger, meaning I still need to rotate in the counterclockwise direction, I end up with a positive value, which means I need a positive rotation. The more important equation for our control law is how do we actually get there? And that amounts to saying, what do we need to set theta dot to? And this is why we have a proportional, this is why we call this a proportional control law. because the value we're setting for theta dot, which is the angular rotation rate of the robot, so how fast are we rotating this wheel forward and how fast are we rotating this wheel backward, it's going to be proportional to, from some constant factor that we'll have to tune, and the current angular error. So if the error is 0, theta dot is 0. If the error is positive, theta dot will need to be positive, and if the error is negative, theta dot will be negative, meaning we would rotate in the clockwise direction. And for a differential drive robot, that's all we need to consider. We'll now look at position control. And so I'll start by just stealing some of the diagram from the previous slide. And erasing the parts we won't need. Now all we care about is our position in the global coordinate frame. So we'll want to define our goal position. One thing to note about position control is that we can't use it directly. We can't translate directly along this straight line without any rotation from the current location to the target location. We could rotate to point at it and then travel in a straight line, but this is position control only, so we're going to ignore any sort of rotations. What'll end up happening is we'll take some sort of arcing path to our target location, our goal location. And there are a lot of different arcs we could take to get there. A lot of different ways we could end up at our target location. And we're going to say that that doesn't matter for this control law that we're going to develop on this slide. The only thing we really care about is that we just don't overshoot our target. So as we get closer to our target, we're going to slow down to make sure we don't overshoot and stop as long as we're within some buffered region of the target itself. I should also mention the same thing here. We don't have to be exactly at this angle. Instead, we'll define some cone around it and say that as long as we're within some range of that cone, we're in a good enough position. But back to our position control, we're going to, just like we had before, start by defining a few extras. The first is the error in our distance. And I'm going to call that delta. And this is not going to be a huge surprise. It's just going to be defined as the Euclidean distance between the 2 points. And it would be appropriate to consider this an error, but I'm going to use the standard notation here and just call it delta for the distance or displacement. And we'll define our velocity. You could also consider this the position, the derivative of position, just like we had the derivative of the angle. But I'll use, again, the standard notation for velocity here. And we'll say that velocity is just equal to k, p, so the constant for position, just like we had a constant for orientation, times this delta value. And before I move on, there are a couple of things we should keep in mind here. we'll put a limit on the maximum value we can have for theta dot. We're not going to assume that the robot can spin sort of at infinite speeds in place. And likewise, we'll put a limit on the same value for v. So in your code, what that should look like in your head is something like v, we compute as kp delta, and then v is equal to minimum of v, and then some threshold value. And same thing for theta dot. Also, it would be impossible if we didn't add those buffers around our goal angle and our goal zone. Just due to floating point math, there's no reason to believe that we could land exactly on this point. Not to mention our sensors and actuators aren't going to be accurate enough to land on a specific point anyway. So instead, we'll always consider this to be some circular region, such that we'll have some code like this. If delta is less than some distance threshold, then we'll consider ourselves at the target. And that puts us into a good place to look at our first full example of controlling to a goal position. And I'll emphasize this position and not pose. Meaning we will be changing the orientation, but we're not going to care about the final orientation.